9.1 Polynomial Models. We start off in this section talking about a particular example of taking a sheet of cardboard or metal and transforming it into an open-topped box. So what we would need to do is we would need to be able to cut out corners, square corners down here, and all the corners needed to be cut out so that you could fold along these lines. So this would be more of a sheet metal example, I guess. And so we start out with a dimension of 80 overall for the piece of metal and a piece of length 60 on this dimension. So we know that volume is created by length times width times height. So we would need the dimension from here all the way over to here. Well, that's 80 minus the 2x's on the ends. And this dimension from here down to here would be 60 minus the 2x's on the ends. So that would comprise the bottom of the box. And of course, when you flip the sides up, these values x would be the height of the box. So we have a length of 80 minus 2x. We have a width of 60 minus 2x. And we have a height of x. We'll multiply these things together. 80 minus 2x. So what do we got there? 4,800 minus 160x minus 120x and plus 4x squared. So that would give me 4x squared minus 280x plus 4,800, and make sure we don't forget to multiply by x. Sorry, I'm running out of room here. So v of x would be 4x cubed minus 280x squared plus 4,800x. Now, if we ask for to calculate the volume, if the dimension that you're going to cut out of the corners is 10, we could do that. So we would take 4 times 10 to the third minus 280 times 10 squared plus 4,800 times 10. And so we would get 24,000. Now, the standard form, I'll try to squeeze all this in here. The standard form for a polynomial in x looks like this. A sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 plus dot 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 a sub 2 times x squared plus a sub 1 times x plus a sub 0. Now let's take a look at all these parts, right? First of all, you should know that standard form, just from Algebra 2, is decreasing order of exponents. You'll notice that the exponents are in decreasing order all the way down to 2, 1, and then x to the 0 at the end. The leading coefficient is a sub n. It's on the leading term, which has the degree of the polynomial. That's the highest exponent. Obviously, a sub n minus 1 would be the coefficient of the second highest term. The coefficient of the second highest term. Now, it could be 0. If there's a missing term, like for instance, if we started out with a to the, let's say we had x to the third minus 7x plus 2. And I asked you for a sub 2. Well, let's see. I see a sub 3 is a 1, and I see a sub 1 is a negative 7, and I see a sub 0 is a 2, but there's no term right there. That means a sub 2 must have been 0. So any missing term in this list has a coefficient of 0. Now, so this is the coefficient of the squared term. This is the coefficient of linear term. Of course, this one on the end is the constant, the plus 5 or whatever. In this case, that right there is a sub 0. Now you're going to use this information in question 5. When you get to question 5 in your homework, you will be using this information, so make sure you pay attention to what we're talking about: leading coefficient, degree, missing terms and coefficients of those missing terms, coefficient of squared terms and linear terms and constant term, degree of the polynomial, those kind of things. Okay, if we jump ahead to example 2, the girl's name in the example is Tamara, or maybe it's Tamara, and she's saving money for her future. Get it? She's saving for Tamara. I know, it's pretty bad. All these names in this book are terrible because they're based on terrible jokes. Not that Tamara's a bad name. Just I know they were trying to make a joke. They're always trying to make a joke out of the names. Okay, like that Mississippi one from the last section or two. I don't know, it's recent. Anyway, so Tamara was saving money. She saved money after her summer of her 8th grade year. She made $600, and so right before she entered her freshman year of high school, she deposited $600 into an account. That account was going to give her 7% interest. Now, at the end of her 9th grade year, the summer after her 9th grade year, she got $900 from working, and she also placed that in the account and making 7% interest. And the same thing happened after her 10th, 11th, and 12th grade year. So this money right here, right here was placed in the account today. So obviously, it has not earned any interest. So, if you are increasing, or you are getting 7% interest, what is your multiplier? What are you multiplying by? Of course, we're multiplying by 1.07. We've talked about that before. It's kind of like the growth factor in an exponential growth function. Well, let's write a polynomial representing this account. Well, let's see here. She started out with $600. that was in the account for how many years? Obviously, 4 years. Then she added to it $900, which sat in the account for 3 years. Then she added $1,100, which sat in the account for 2 years. And then she added $1,500, which sat in the account for 1 year. And then today, well, today she deposited $1,600 because this is right after the summer of her senior year. So, this amount of money. Well, one way we could do this, and that one way would be to use the 600 times 1.07 to the fourth plus 900 times 1.07 to the third plus 1100 times 1.07 to the second plus 1500 times 1.07 to the first plus 1600. So the total there, is $6,353.41. They're probably not going to give you the extra penny, so you're probably going to round down. But we won't worry about that for right now. $6,353.41, approximate value. Now, another way to do that, let's go up here to the y equals. Let's type an equation in here. Now, what kind of polynomial would we want? We would want 600 x to the fourth plus 900 x to the third plus 1100 times x squared plus 1500x plus 1600. There's your polynomial. So this question asked me to write a polynomial representing the account. There it is. Now, we've talked about setting up tables, finding values. Right now I have my calculator set for the independent variable to ask. That's under the table setup. So now I can go over here to the table. And I can say, well, what happens if I use an x value of 1.07? Oh, 6,350. Oh, there it is. That value we just typed in. So we can use the polynomial. Hey, what happens if I got a 10% rate? How much would it change by? So it makes it nice and convenient. What if I only got a 3% rate? So using that polynomial function, y equals 600 x to the fourth plus 900x cubed plus 1100x squared plus 1500x plus 1600. There you go. You got your polynomial representing the account. You pick a different value to put in for x, we get a different number. Now, a couple more things to talk about in this section. Degree of a polynomial. The degree of a polynomial in more than one variable is the largest sum of the exponents in one term. So, I notice here, 2 plus 3, that means this is a fifth degree polynomial. 2 plus 2 adds up to 4, but I see a 5 over here, so this is also a fifth degree polynomial. We did problems where we talked about, we'll do some more problems like in, once we get to the Chapter 10 stuff that involve more than one variable. It has to do with the binomial distribution, but that's pretty much just like making a free throw, missing a free throw, heads, tails, that kind of stuff. So that'll be, you'll see some of that again. We've seen a little bit of it when we did Pascal's triangle. They refresh your memory about the volume of a cube, and they give dimensions of a plus b. It's not that challenging. I hesitated on even showing you this because it is so basic. So I multiplied those two together. Got a squared plus 2ab plus b squared. And then I multiply again by a plus b. The boxes do come in handy, especially as you get higher powers. And then I know what some of you were thinking. Couldn't I just use something that I've learned before? Huh. I wonder what you mean. Couldn't I have just used good old Pasquale's triangle? Of course! Of course. 1, 3, 3, 1. A to the third, a to the second, a to the first, a to the 0. B to the third, b to the second, b to the first, b to the 0. A to the third plus 3a squared b plus 3ab squared plus b to the third. Of course we can do that, because we are good like that. All right. See you in class.